Welcome to the 24-23 video series. In this video I'll be discussing or giving a theoretical background of distillation, which is one of the more common ways of separating liquids in laboratories based on differences in boiling point. I'm going to start with a review of Raoults Law. Raoults Law states that as we learned in general chemistry, that the vapor pressure of a solution of a non-volatile solute is equal to the mole fraction of the solvent in the solution, that's the volatile portion of the solution, times the vapor pressure of the pure solvent. And so what that means, of course, is that the vapor pressure of a solution will be less, a solution of a non-volatile solute, that is, will be less than the vapor pressure of the pure solvent. Consider the effect that has on the boiling point of the solvent. If you're reducing the vapor pressure, it takes more heat to raise the vapor pressure of the solution to atmospheric pressure, which is the definition of normal boiling point, than it would for the pure solvent. And so therefore the boiling point of a solution of a non-volatile solute is higher than the boiling point of the pure solvent. That's not so important in distillation though. What's more important is the temperature of the vapor above the solution. So what I'd like you to consider and think about is what effect does the non-volatile solute have on the temperature of the vapor above a solution, considering the fact that the non-volatile solute is not volatile and is not present in the vapor above the solution. And we'll talk more about that in the second video on distillation, where I discuss the procedure of distillation. So one thing that we didn't cover in general chemistry, at least not in my courses, was Raoults Law for solutions of more than one volatile components, or two or more volatile components. And Raoults Law is very easily modified to deal with that situation. So the total vapor pressure of the solution, and you see that right there in this equation, is equal to the mole fraction of a volatile component A, so that's going to be one of your liquid components, times the vapor pressure of pure A, plus the mole fraction of volatile component B, so that'd be another liquid, times the vapor pressure of pure B, and so on for every one of the volatile components in the solution. So it's really a pretty straightforward expression. So we can calculate the composition of the vapor phase above a liquid, because when you're boiling or distilling a solution of more than one volatile component, the vapor will contain, since both components are volatile, the vapor above the solution will contain both components, or all the components, if they're all volatile. So what we're going to look at down below here. So this is the phase diagram for a two-component solution. That is a solution of two volatile components. And so the y-axis here is temperature in degrees Celsius. And so what we have here is the boiling point of the second component. That's 90 degrees. So that's the higher boiling point component. So this is B. This is the boiling point of B. I should probably have labeled that. So this is the boiling point of B. And this is the boiling point of A over here, which is the lower boiling point component, which is 50 degrees. So we can calculate the composition of the vapor phase above this solution at any one of these compositions. So the x-axis is composition, so we're starting with 0% A over here. This is actually, I got those reversed, of course. So this is 100% B, this would be the boiling point of B, and this would be the boiling point of A over here. So we've got boiling point of B and boiling point of A. So again, we can calculate the composition of the vapor above a liquid at any point by just rearranging Raoults Law in terms of the mole fraction. So this will get mole fraction of A is equal to vapor pressure of volatile component A over the vapor pressure of the solution. Vapor pressure of the solution is going to be atmospheric pressure unless you're doing a vacuum distillation, which is done when you lower the pressure above the solution with a vacuum source. So the top curve in this phase diagram here is the vapor composition. It's the composition of the vapor phase. And the bottom curve here is the composition of the liquid. So this curve can be calculated at any point from this equation, the top curve. And of course the liquid composition is just the composition of the flask at any given point. So let's take a look at what happens during a distillation. We've got two volatile components like this. And so I've got that. Let me scroll down a little bit. There are two types of distillation. So there are simple distillations. And a simple distillation is a distillation where there's essentially one theoretical plate. And a theoretical plate, that's a term I expect you to be familiar with. It's a very important term in distillation, is simply a cycle of vaporization and condensation. So you boil a liquid, it vaporizes, and when it recondenses, that's one theoretical plate. So let's assume that we're doing a simple distillation of this two-component mixture, and we're starting with 75% A right here, this composition right here, and let's see, 25% B. So we'll draw a line. The liquid composition is 75-25. And so the vapor composition, to figure that out, we can plug into that equation. What we're going to get, we'll draw a line all the way over here, as horizontally as I can make it. So right here would be the composition of the vapor above the liquid if you started with a 75-25% solution, 75% A, 25% B. And you'll note that the vapor is greatly enriched in A, which makes sense because A has a lower boiling point, 50 degrees versus 90 degrees, than does B. And so it's got a higher vapor pressure. You'll have more A in the solution. So, important point here, though, is that because both of the components have vapor pressures, when this condenses, you don't have a pure mixture. What you've got is a mixture. This looks like it could be maybe 20% A right here. So this might be approximately 20% and 80%. So we've greatly enriched the resulting solution in component A, or component B rather, but it's not pure. And for this reason, we don't tend to do simple distillations with solutions that have more than one volatile component in there. So simple distillations are if you want to purify a liquid, are pretty much reserved for solutions where you have a non-volatile solute. So in that case, the solute, like salt water, for example, doesn't have a vapor pressure, and so whatever's evaporating, whatever's boiling off, is your pure solvent. So that's the problem with a simple distillation if you've got more than one volatile component. The second type of distillation is a fractional distillation. And in a fractional distillation, and we'll draw a diagram of this in the second video on distillation, on the procedure of distillation, the vapor is going to pass through a long column. It's filled with an inert material. And as the vapor passes through that column of the inert material, it will condense on the inert material and then revaporize because the hot vapor is transferring the heat onto the inert material. It heats up over time and until it reaches the boiling point of the liquid again. And the liquid re-evaporates, re-vaporizes, goes up the column a little bit farther, cools down, recondenses, and it does that over and over again on the column. And so you get multiple theoretical plates with a fractional distillation. So in the second vaporization cycle, we've greatly enriched the vapor, and so we're 90-something% at this point, after two theoretical plates. There's a big difference in the boiling points here, so it doesn't take too many theoretical plates in this example. And so one more vaporization will take us to our pure B. And so after a couple, maybe three or four theoretical plates on your column, we've completely removed A and have pure B. And so if that condenses out into the receiving flask, you've successfully separated the two compounds. So for solutions of more than one volatile component, we use fractional distillations. It gives us multiple theoretical plates, which enables us to separate the compounds. So theoretically, you could separate any two liquids, any two compounds that have any difference in boiling point with enough theoretical plates. In reality, however, that's not always possible. And the reason is shown down below here, because some compounds exist as make solutions that are known as azeotropes, mixtures known as azeotropes. Azeotrope is a mixture of volatile liquids that cannot be completely separated by distillation. So azeotropes don't conform to Raoults Law. They are extreme deviations from Raoults Law. There can be minor deviations from Raoults Law as well, but an azeotrope has an extreme deviation from Raoults Law. Azeotropes form a mixture of constant composition and boiling point, and that's why after a certain point they can't be separated. There are two types of azeotropes. The first type we'll talk about is a low boiling point azeotrope. And these form because Raoults Law assumes that there is essentially the same attraction between solute and solvent particles in terms of the interparticle forces, the intermolecular forces, as there are between the solvent particles themselves and the solute particles themselves. And of course, that's not always the case. So if there's a smaller attraction between the solute and solvent particles than it would be predicted in an ideal solution, which is a solution that's described adequately by Raoults Law, the phase diagram, the curves in the phase diagram bow downward like this. And so you reach a point if the deviation is extreme enough where you get a kink in the curves, that is the curves for the vapor composition and the liquid composition come together at a certain point, and that is the azeotropic composition. So right there is the composition of this particular azeotrope of compounds or liquids C and D. So what happens if you start with, say, maybe a 25, this looks like maybe a 30% solution of C, and the remaining 70% is D. So we go up, composition of the liquid is 70-30, 30-70, and so when it vaporizes, it's going to go in that direction now, and so this is the composition of the vapor. If we're doing a fractional distillation, as we should be, this will be the composition of the liquid when the vapor condenses, and then we go over another theoretical plate, and another cycle, and eventually we reach this point here, which is the azeotropic composition. You can't get past that. So at this point, when the liquid vaporizes, it's going to be at this particular temperature and at this composition forever. You can have an infinite number of theoretical plates. You can't get past this point. You're at the azeotropic composition. Same thing would happen over here. So let's say we started at 90% B here and 10% C. So if we go up in this direction, there's the composition of the liquid. There's the composition of the vapor, and after a few theoretical plates, we reach the azeotropic composition again. And so the vapor can never be purified. You always reach the azeotropic composition. It's important to note, though, that the liquid can be purified. In other words, the liquid is going in this direction when the vapor is going this way. So with every theoretical plate, the liquid remaining, there's less and less of the lower boiling point component remaining in the liquid. So eventually you boil off all of the lower boiling point component, and you will have your pure C or pure D left in the flask. Same thing over here. So with every theoretical plate, the liquid becomes more and more enriched in D. So you'll end up with pure C on this side if you boil off all the D. You'll end up with pure D on this side if you boil off all the C. It's the vapor that can't be separated. You eventually reach the azeotropic composition. So the other type of azeotrope is a high boiling point azeotrope. And in this case, the interaction, the intermolecular forces between the two volatile components is stronger than you would predict. It's stronger than you have among the components themselves. So in other words, the attractive forces between E and F are stronger than the attractive forces between molecules of E and F and F. That causes the composition curves to bow upward until, in an extreme case, you get a kink, and that extreme case is a high boiling point azeotrope. So let's take a look at what happens in this case. So we'll start at about this composition. Maybe I'll start out here. So this is, I don't know, maybe roughly 50%, I guess, 50-50 mixture of E and F in this case. So there's our 50-50 liquid composition. And we always go in the direction of enriched vapor, and the vapor's enriched in the lower boiling point. So this is the boiling point of E down here. This is the boiling point of F. So one theoretical plate, this is our new liquid composition. Another theoretical plate on our column, and that's our new composition, and one or two more brings us to pure E coming off. But again, it's important to note that as the vapor is getting pure here, the liquid is going in this direction. As more and more of the vapor of the lower component, the boiling point component E, gets boiled off, the composition of the liquid goes up in this direction until eventually it reaches the azeotropic composition right there. And at that point, when we reach the kink, the liquid has got a constant boiling point and a constant composition, and you're not going to get any more separation of the two components. So you'll get an azeotrope boiling off at this point where the composition never changes. Similarly, if we were to have started at a composition over here, where that'd be 20% E and 80% F, once again, going in the direction of enrichment in the lower boiling point fraction, one or two theoretical plates takes us to pure F. So the vapor coming off at this point is pure F. But as that vapor comes off, again, the liquid is becoming enriched in component E here, which brings us up to the azeotropic composition again. And you no longer get any separation at this point. At this composition, the azeotropic composition, the liquid boils at a constant temperature and both components come off in this ratio, whatever that is. It looks like maybe 75% or 25% E and 75% F at the azeotropic composition there. So the point is here that in some cases you get a low boiling point azeotrope, and the boiling point of a lower boiling point azeotrope is below the boiling points of both pure components. And in some cases, some azeotropes are high boiling point azeotropes, in which the boiling point at the azeotropic composition is above the boiling points of both components. But at that composition, you cannot separate the two compounds. And sometimes there are actually azeotropes that are three components, and maybe even beyond that. So not all azeotropic mixtures are just two components like this. But the point is, once you reach that azeotropic composition, you cannot separate. So we cannot adequately and always separate all compounds by distillation, even if there's a significant difference in their boiling points. So that's it for the background. I hope that makes sense, and let me know if you have any questions. And please make sure that you watch the second video, the other video on distillation, which goes over the procedure you'll be using in the laboratory.